All right. Good morning, everybody. Okay. I'm just going to load everything up, so give me a minute. Let me turn my volume up so I can hear y'all.
If you mad something, because it kind of still kind of like strong a little bit, huh?
Yeah, it kind of is. Oh, I have to do another two-step verification. Come on. Where's my verification? There it is. Okay.
You know in my throat.
So I'm gonna need that. I'm gonna throw the attendance up real quick. If y'all give me a minute. Okay. So I need to share my screen. Okay. Oh, and we got somebody saying something on the chat. It's okay. Jennifer, I'm not gonna look. Oh, that's not what I wanted. Here we go. So first things first, we're gonna check in. I feel like I'm too short. I need to grow a few inches. Let's see if clicker comes up. Ah, there we go. I need the Jeopardy soundtrack while y'all are waiting on me. Something like that. All right, so we're gonna start class. There we go. And we'll do this first. Okay. There's so much on the screen. Okay, let's try that. Oh, that's not what I wanted to do. There you go. So everybody can check in on attendance. So I'll give y'all a few minutes just to get that done, and then we're gonna get started. So I'm gonna close this. Oh, let me hide this. So much. Hide floating meeting controls. Okay. Exit. And we want to be on clicker questions. Was it already Google Slides? Oh yeah, I want to open with Google Slides. Okay, I think, I'm trying to see. Y'all don't look. Try to see how far we got. Yeah, we did that one. We did that one. Yeah, we did that one. Okay, I think this is the last one we did. Okay, so Ross, you got your thing. Okay, good. Awesome. Okay, do we have about, it says everybody checked in. If you have not checked in, you need to check in because we're going to start very soon. Let's see our participants. Here. So we have 55 participants. So it's 54, 55. Okay, that should be good. That should be everybody. All right. And all right, let me turn this down just a little bit. Nobody's in the classroom today, so I'm actually going to take my mask off because no one is in here. Oh my gosh, I don't have to wear a shield or a mask. This is amazing. All right. So I'm going to manage the chat as best I can all by myself. So we were talking about our different problems. So I'd like for us to do a few more clicker question problems. But before we start on that, I actually wanted to show you one thing. On Moodle, if you go to Moodle, right? If you go to our class, I put you a little announcement. And why did my chat go away? Violating, I know, I'm violating the rules as long as I am not, nobody's here and they just sanitized the room, so I'm good. I'm excited. All right, so extra resources. A couple of people asked me for some extra resources as thermochemistry and kind of an acid-base refresher. So I did that for you. I went and looked and dug through Khan Academy. Khan Academy is good. So when you kind of go, oh, I've seen that, but it's been a while since I've seen that, then Khan Academy is a good place to go. So I did you a link to, and it's a couple of different things. It's not just one video. It's kind of a range of videos. I'm going to show you real quick, maybe. But you can kind of just pick and choose the ones that you really want. Like, you probably don't need the first law of thermodynamics introduction, but there are some other things that you might like, specific heat and temperature, that might be good. Oh, enthalpy, heat of formation, Hess's law, those things that, oh, that might have been something I should have gotten in Chem 1. Entropy, right? Remember enthalpy and entropy? Okay, so this kind of gives you the chance to pick and choose what you need for you, and then gives free energy. Okay, so, and the same thing's true about the acid and bases. So you just kind of have to look through a little bit and see what you want. Okay, any questions on that? All right, and you can give me a thumbs up if you'd like. I'd love to see some thumbs up. I don't know how that's going to show up, but I'm guessing everybody's good. If I don't see a comment from you, I'm going to guess that's good. Okay, so we're going to go back and we're going to do some clicker questions. I think these helped y'all out, hopefully, pretty well. All right, so I'm going to stop this poll. Oh, we have 57 responses. We had a few people come in. Okay, so that's what I'm looking for when we all do this is 57 responses. All right, so let's try something new. Now, this has to do with our adenylate system. So I'm telling you that mutations in an adenylate cyclase kinase, you have to remember, and you might have to crack your book open where you are and go and see exactly which reaction adenylate cyclase catalyzes. But if you have mutations in this enzyme, it's going to lead to a hyperactive enzyme. So it's going to be more active than it should be. That ultimately ends up elevating ADP levels in the cell. You need to calculate the energy charge of the cell following these atypical adenylate concentrations. Okay, so here are our concentrations. There's a formula that you can find in the book that you need to use in order to answer this question. Okay, so find your formula. Plug it in. And then it's just a numeric response. So those who can type it in a numeric response, please do. But if you can't, it's okay. Just write it down.
Is this supposed to?
Ask me again. Oh, I'm supposed to be a, oh, y'all are right. Numeric. Thank you. Numeric. Thank y'all. Try again. Answer again. I'm going to go close the door to the hallway so that I have less noise. I'll give y'all until 2 minutes. I only have 37 responses. I guess I'll give you a top 3. Okay, if you don't have an answer, type something. All right, here we go. So, oh, all right. So what you should have gotten is something that's about, that's really, really off. Stop doing that. If I could show my equation at the bottom. When you do this, all you're doing is plugging and chugging. All you're doing is adding in your values into this formula down here, which I can't see because of, there you go. Okay, this is gonna drive me crazy. So don't use the mouse. So you plug it into this formula, right? Now, what should the EC be for the cell normally? for normal cell? Y'all put it into the chat. What should your EC normally be? It's a range. Come on, y'all. Yep, 0.7 to 0.9, right? Are we there between 0.7 and 0.9? Absolutely not. Absolutely not. So we know this is a really, really atypical cell, right? Because we don't have the normal proportions of each of our pieces of the adenylate system. So where does adenylate cyclase behave in the adenylate system? If you're going to elevate ADP levels, remember it's involved in recycling. So what are you going to do? Anybody know? What's our equation that adenylate cyclase catalyzes? You can go and look it up. Give y'all a second to go look it up. Because there are two reactions in the recycling of ATP. I put the equation. Oh, do I have, is that my old answer? 34.5? I bet I did. I bet I just left it. So I bet I just left it from the last one. So what did you get? 0. Let me see. Let me go up. Oh, I wasn't, y'all were typing and I wasn't seeing it. 0.516. Okay. 0.516. And let's see. If I can scroll through this. I think I need to see where I am. Oh, there it is. Okay. All right, good. Good. Here we go. So we got it. All right. So we're going from AMP, good, plus ATP. We're going to 2-ADP. So if you have a mutant adenylate cyclase that makes it active, what you're going to do is you're going to increase the amount of product. So you'll have too much ADP, you'll have not enough ATP, and not enough AMP. So you end up with your abnormal EC concentration, right? Okay, so now we're going to use this information and we're going to incorporate it into the next question. And I did find a trick for when you want to erase. Oh, but I think I'm covering it. Here we go. I can clear all. All right. See, I did learn something new. Okay. So for cells that have this hyperactive adenylate cyclase, right? Now, what if we reverted that hyperactive adenylate cyclase mutation? What if we went back to the normal conditions? How would you expect the energy charge of the cell to change? And what did we say with the mutant? It was about 0.5. So what would you expect to happen? Here's my thing. Multiple choice. Ooh. And I think I'm covering this stuff. There we go. We're looking for 59 responses. Okay. I'm calling it at a minute, so 5 seconds. Okay, so what do we all say? All right, so the majority said A. The majority said A. You would expect the EC to increase. Why would you expect the EC to increase? You expect the EC to increase because this is our reaction, right, that we just said that adenylate cyclase catalyzes. So for a normal cell, if you produce less, if you produce less of this, what's going to happen? Our concentration of ATP is going to go up, right? And so because we know our mathematical formula for the EC, we can predict what would happen, and we would predict that this would lead to a ratio that's closer to 1. And so it would increase over time. Does that make sense? It's hard for me not to see all faces, even if they're covered with a mask. Good? Okay, unless somebody puts me a comment, I'm gonna assume good. Otherwise, tell me. All right, so I'm gonna clear this, clear ink. Okay, so of our 3 thermodynamic quantities, delta G, delta H, delta S, which is more useful in determining spontaneity of a reaction? For everything we said. I thought you said. No. So Jaslyn, when in the previous question, where are we? So in the previous question, what we says for cells without the hyperactive adenylate cyclase. So you had the mutant, and you went from mutant to normal, right? In the mutant, you have extra, but now we're talking about normal. Okay. Okay. All right, I'm calling it at a minute, so 3 seconds. Okay, so what do you expect? You expect that our delta G is going to be the most important, right? What's our formula? Delta G is equal to what? You have to know this formula. You have to know this formula. What's your formula? Y'all put it in the chat. You have to respond in the chat, y'all. You have to be engaged.
Delta H minus T delta S.
Good, yes.
Yep.
Okay, so the way that I remember the orientation is I call this my ghetto homies. That's how I remember the orientation of G, H, T, and S, ghetto homies. One of those things. But remember, we said that we use this equation to get higher test scores. Oh, nice. Very nice. Very nice. Yes, if you know this formula, you will get higher test scores. So we know that we use this formula to determine delta G, because we talked about the last time, right? What happens if delta G is positive? Because we have 3 conditions, delta G 0, delta G negative. Non-spontaneous, non-spontaneous. Delta G negative tells us that we are spontaneous, and if delta G is equal to 0, we know that's our switching point. That's our pivot point, right? So the important thing to know is that even though you're going to use delta G to predict if it's spontaneous or not, it does not mean that it's going to happen quickly. So things that happen very slowly are also spontaneous. Like, how long does it take something to rust? It takes a while. It takes a while for that to accumulate. So we are not talking about the rate of a reaction. So be very careful that you understand the difference between spontaneity and reaction rate. Reaction rate is how quickly the reaction will proceed. Spontaneity is, will it proceed on its own, or do we need to couple it to something to make it go? So be careful with that, with those terms. Okay, let me see if I can clear my ink. Okay, so now you're going to tell me whether the group circled in red contains a hydrogen bond acceptor or a hydrogen bond donor. This one should be easy. And y'all know y'all can come keep me company in the classroom. It's open. There's no one here. You could come and be in the classroom if you want on our virtual days. I'm not saying you have to. I'm just saying you don't have to sit in your car or wherever you are. If you're on campus, you have a place. Just saying. All right, Hannah, I'll see you next Friday. We just can't have more than 32 people, but I'm figuring no more than 32 people are going to decide to want to come. So I think we're going to be okay. All right, Ross, sounds good. Especially y'all who have me for lab. Okay, oh, it's a minute. I need to pull it. All right, here we go. So, all right, so what do we say? Oh, wait, how did I do that? Here we go. Okay, so what we are looking at here, this is an acceptor. So what's the definition of a bond acceptor versus a bond donor? Oh, you don't have to, Annie, you don't have to. I'm not. Nobody has to be here, right? A hydrogen bond a hydrogen bond acceptor is going to be one that's very electronegative. So it's going to be very attracted to the positive charge on the hydrogen. So here, right, we have this electronegative oxygen and it's participating in this hydrogen bond, right? So my donor would have been this nitrogen, my acceptor is the oxygen, right? Oxygen's lone pair, yep, attracts, doesn't take. I hate the word hydrogen bond, but it's attracted to, yes. Okay, so here are a couple of more. I want you to just look at these real quick. I'm gonna move the chat over to the side. It's not a clicker question, but look at these and see which ones you think are acceptors and which ones you think are donors. It is a proton, it's positive. It's the part of the hydrogen that's positive is a proton. Ross was saying electron. No, they have electrons, and they are very electronegative. Yeah. Okay, so take a look at these and identify which ones are hydrogen bond acceptors and which ones are hydrogen bond donors. Just take a second. Okay, so what you should have come up with is that these two are acceptors, right? Are very, very electronegative oxygen, and oxygen wants to pull that hydrogen, right? Over here, here's our acceptor, so here's our donor, right? Now this case is a little bit interesting, right? Where we have two oxygens, but here we have the oxygen attached to a hydrogen. So this one's going to be the donor, this one's going to be the acceptor. So we have acceptor and donor. Okay. All right. Ooh, clear the screen. Ah. Make it stop. All right. What is the pH of an aqueous solution of 300 millimolar HCl? So when you're doing this kind of a problem, the first thing that you need to figure out with your acids and bases are what kind of an acid and base is this? What is HCl? Is it a strong acid, a weak acid, or are we talking about a buffer? Those are our only three. This is a strong acid. Anybody know all your strong acids? Y'all should know y'all strong acids. Do you know your strong acids? I bring clay, right? Okay, I bring clay. So what does that mean? HI, HBr, HCl, these are our binary strong acids. And if your rebaf is not working, it's okay. You're okay. It's all right. Just put it in the chat. It's fine. Okay, and then we have to worry about our tertiary acids, the ones that have polyatomic ions in them. So when you look at that, you're looking at oxygen to hydrogen ratio. If you have 2 or more oxygens to hydrogens, then you are strong. Okay? Yes, yes, I see people typing. Yes, so do you see in here where we're looking at CH2SO4? H2SO4. What is that telling us? That we have 2 to 1 oxygen to hydrogen. So we are strong. That is correct. Good. Good, good. Okay. But that's my little, this is my little, I bring clay and then 2 or more oxygens to hydrogens. That's my little remembering tool. Okay, so let's try to answer this one, and this one's going to be numeric. Let me clear this. So, numeric. Here we go. So now you know that it's strong. How do you calculate the pH? This one shouldn't take you long, so I give you about a minute and a half. A minute and a half, I'm calling it. Okay, minute and a half. All right, so let's stop. Let's see what we got. Okay, so 0.52 is what we're looking at. Okay, so how did you know that? If HCl is a strong acid, what's going to happen when you put it in water? What's it going to turn into? Oh, okay, that's all right. Okay, so what is it going to turn into? It disassociates. It's a simple disassociation. So you're going to get H+ ions and you're going to get chlorine ions, right? Okay. How much of this HCl disassociates? All of it. It's strong. That is the definition of a strong acid. So we don't have, you know how weak acids, we have these double arrow, right? Because only part of it disassociates and it's in equilibrium and all that kind of stuff. We don't have that with a strong acid. With a strong acid, everything disassociates. So if you can find out the concentration of the acid, you can find out the concentration of the hydrogen ion. And from that, we know the pH is just a negative log of the concentration of H+. And so you can find your pH. So that is the easiest one you're going to see. Can pH? Yes, technically it can, but you're not going to see that. We're not doing that. But technically it can, yes. Okay, so here's my second part. This is part B, if I can clear the ink. Okay, so what is the concentration of OH minus in the same aqueous solution? So we're talking about the same situation, but I want to know now concentration of OH minus. Give y'all about a minute and a half. maybe more. It is so quiet. It is quiet. We actually do need some sound. It's kind of strange for me. I'm kind of used to having everybody in here, especially from last time when we had all the music in the quad. That's why I need that. That's why I was saying I need the Jeopardy soundtrack. You know, if I'm asking y'all all these questions, you need a soundtrack to solving the problems. So, but I feel like that's one more electronic that I do not need to try to manage. Mine said invalid response. LOL, it's okay. Okay, Ross, you're probably right. Less distractions. I'll be quiet. Mine also said invalid. Is it a number? It's numeric. I don't know. I could put the answer in that one. Oh, maybe it's the caret. Maybe it's the caret. Try it without this thing right here. See what happens. Oh, use the E sign. Okay. Okay. We're learning things today. All right, I'm calling it at 3 minutes because it seems like everybody's kind of got the answer. Yay, it worked. Okay. So what you should have gotten was those are non-significant. That's not significant. You can't do that. You don't have that many significant figures, but technically that answer is correct. Too many significant figures. But yeah, close enough. Okay, y'all were well. It's supposed to be 14, not 13. But that's okay. Okay. It adds the zeros itself? Oh, that's crazy. Okay, that's weird. All right, so when you're doing this, what do we know about the relationship between pH and POH? We know pH plus POH is equal to 14 because we know the equilibrium constant for water, kW, right? What is kW? 1 times 10 to the, help me out, negative 14, that's right. So we know that if we take the negative log, right, we're gonna get 14. So we know if we take the pH plus the POH, we get 14. So we can use that simple relationship and find the POH. So if this is the POH, are you done? Because this would be an answer choice. This could easily be an answer choice, right? You're not done. That's the POH, but that is not the concentration of our hydronium ion, right? So we have to convert that. How do we convert that? We take the negative log. Okay? All right. Let's try one a little more complicated. This is a little more complicated, as you can see, right? So here we have an acid. It's a phosphoric acid, right? Correctly labeled the most abundant species. Oh, Dana. Okay, what you got, Dana? Let me go back. What you got, Dana? 1.2. Anybody else get that? For which part? Your calculator, Dana, 1.12 for what part? How do you put it into the calculator? How do you put what into the calculator?
I did the negative log of the 13.48. Is that how I'm supposed to put it in?
Yes. The POH, it would be like 13.48 is equal to the negative log of the concentration of OH minus, right? So then how do you get rid of a negative log? It's the anti-log. So you're gonna raise it. So you're gonna do your calculator, it's like second log, and it's 10 to the, right? And then you do that to the negative 13.48, right? Because you move the negative sign over first, and then how do you get rid of the log? is by doing 10 to the.
Okay, I see it. I'll put it in as 10 to the negative 13.48, and I got the numbers.
Awesome. Yep. The opposite of the log is 10 to the. Good. So everybody good on that one? I can go on? Yes, good. Of course, y'all just stop me. If I ever do that, y'all just stop me. I tend to just go on, so just stop me. Okay, so now we're going to talk about something a little more complicated. If you look at a titration curve and you see this, what kind of an acid do you know this is? Anybody? Nope, not strong. Polyprotic. Polyprotic. It is polyprotic. What does polyprotic mean? It means that we can have different numbers of hydrogens attached to our functional unit there, right? Multiple hydrogens, right, exactly. So a lot of times we use these polyprotic acids in creating buffers. And that's what y'all are actually going to do in lab, or some have already done in lab. Yes, is making buffers. So a lot of times we use a polyprotic acid. And what we do is we find the point at which we have our pKa.
Yeah,
And so,
It means
go ahead.
multiple times.
Somebody have a question? It's a background noise. Okay. So what happens is that you can, each of these equivalence points is where you are losing or gaining a hydrogen. So what I'm asking you for this polyprotic phosphoric acid is, what acid do we actually find in this range? So what species is most predominant here, 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 and here? So for the first one, I want you to identify just this one. Just identify number 3. So tell me A, B, C, or D. I'm going to switch this to multiple choice. Which acid do you think is present right here at step number 3? What is the predominant species? I'm going to clear this. Calling it at 45 seconds. Okay, so what you should have gotten, stop. Oh, we got answers all over the place. What we should have gotten, sorry, is C. We should have gotten C. So if C is HPO4 2-, what's going to happen when we go to 4? We're adding more sodium hydroxide. So what's going to happen if I have HPO4 2-, minus, not a plus, come on, 2-, if I add NaOH, what's going to happen? So what happens is this disassociates, right? So you have Na plus and you have OH minus. So what's going to happen is that this OH minus is going to come over here and steal our hydrogen, right? So you're going to lose that last hydrogen. So now I want you to think about it for just a second and tell me, I'm not going to do a multiple choice because there are too many, but what's the order? What should 4 be? What should 2 be? What should 1 be? So like, just jot it down. Yeah, what's your start? So your start should be number 1, right? Okay, so what you should end up with at all points, we should go B should be our first one. So we have our most number of hydrogens. Then as we add sodium hydroxide, that sodium hydroxide is going to steal away a hydrogen and steal away until we get to our unprotonated form. Good, good, very good. All right, so we're okay on polyprotic acids. We understand how they work. You went backwards. Yep, that's okay. That's okay. So whenever we're picking this as a buffering system, what you want to remember is that you can only buffer a small range of pH values, right? Because once you add too much sodium hydroxide, you're going to change the species of that polyprotic acid, and you're no longer going to be able to keep it in a particular buffering range. You're going to take away those hydrogens, and you're going to have way more OHs floating around, and so that's going to change your pH and bring your pH up, right? So it only works for a certain range, and you're going to do way more detail on acids and bases in lab. Oh, let me clear this. Okay, so what would the pKa of a weak acid be if the ratio of the unprotonated form to the protonated form is 50 in an aqueous solution at pH 6.5? Oh, Dana. The definition for polyprotic? Oh, and let me do this numeric. Y'all can work on that. Okay. The definition of a polyprotic acid is an acid that has multiple forms that can have multiple hydrogens, right? So polyprotic meaning multi, Ti, hydrogens. So think about, for this one, how are you going to solve for that pKa? There's a particular formula you need to go and find. It's in your book. Are we really already 11:30? Ah, Henderson-Hasselbalch, yeah. You know, the Henderson-Hasselbalch, that always makes me think of, what's the guy's name? David Hasselhoff. I don't know why. It just makes me think of that. Okay, so I'll give you all about till 3 minutes, so another 30 seconds. Okay, if you add chapter 3 slides. Did I not yet? Maybe I converted them to PDF and I haven't uploaded them. I can add the chapter 3 slides today. I'll go and add them. I did not. Okay, I will go and add them. I will go and add them right now. Well, not right now, but after class. Chapter 3 is awesome. I love chapter 3. I'm super excited. You said every chapter, yes, I probably do. Is it, no, it's not so many calculations. It's all DNA. It's awesome. It's super interesting. And I am going to say that every chapter, and it's true. All right, so I'm calling it 4 minutes. I was supposed to call it 3.5. I'm calling it at 4. Okay. All right, so you good, 4.8. Good, good, good. Okay, and we do have some close values. Yeah, I'll give you that. All right, so where can we get extra practice with these equations? The Khan Academy has some good ones, and Lab's going to give you lots of practice with these equations, right? Okay, so this is Henderson Hasselbalch, right? And the lab book, that's exactly right, in the lab book. Very good. Okay, so what we're trying to solve for is the pKa. So all you have to do is rearrange in order to solve for pKa. You can't see the slide fully. Oh, because of the thing. I know, every time I move the mouse. Okay, so this is our standard formula, right? So we want to put pKa by itself. So when we rearrange and we get pKa by itself, all you have to worry about now is this ratio. So the ratio, does this have to be, what kind of a ratio can this be? If we're saying the ratio of, and I guess I can move the chat too, right? What we have in the question is the ratio of the unprotonated form to the protonated form is 50. So what's my unprotonated form? A minus or HA? Unprotonated. A minus. So this is unprotonated, right? So this one is protonated. What values could I put in there? Let's say I was given a lot of values in the problem. What I could put in there are moles, right? Moles would work, or molarity. It doesn't matter really what the unit is because it's the same unit on the top as the bottom, and so the units will cancel out. So what you end up with is a ratio without a unit. So if we're told that the ratio is 50, right? That's just telling us it's 50 over 1. Unitless doesn't make a difference. And we can use that to determine our pKa. So anytime you have that weak acid, and you're doing a ratio of protonated and non-protonated, then you can use Henderson-Hasselbalch. Okay? Yeah? All right. So let's try one more. All right. How much lactic acid, and here's our proton donor, like this is the hydrogen that's actually going to be donated, is present in an aqueous solution of pH 5.1 if the concentration of our lactate, which is our proton acceptor, is 0.2 molar and the pKa of lactic acid is 3.9. Oh, I got to do this as a numeric. Okay. You tell me, this is one of the things that you have to decide is which equation you need to use. So look at the Henderson-Hasselbalch and see if you can plug everything in and have one unknown left over. So that's a decision you have to make, Ross. Okay, I'll give you till 3 minutes. Ten seconds. Okay. So what do we get? Ooh, good. We got some. Some of these are close, right? Okay. So what did you do? I don't know how to make all this fit on the page. Okay, so we are going to use Henderson-Hasselbalch again, right? So now what do we have to do? We have to rearrange for one of our unknowns. We're asked how much of the proton donor, the lactic acid itself, is present. So we're trying to solve, I need to stop doing that. We're trying to solve for this unknown right here. So you need to be able to rearrange your formula. So what we're able to get is our log of the concentration of the ratio of the two concentrations, right? But what you have to remember is that you were given a concentration for our proton acceptor. And so once you have that, now you can plug in and you can solve for your concentration of lactic acid. Okay? So our first answer here, we're told that this is the ratio. But we need to actually solve for our real concentration of lactic acid. So it's kind of like a two-step. Questions on that one? What kind of a system, acid-base system, is this? Where we have both the donor and the acceptor. What do we call that? Somebody? Anybody? What do we call that? You're going to do some in lab, or you already have. A buffer, a buffer, a buffer. Yes, good. Good. Okay, I want to show you one thing because we're getting close to the end already. Is it really 11:40 already? This class flies by because I love it so much. Okay, I want to, oh, I could show you this one. This is really the last question. I'm going to show you this last question real quick, and I'm going to show you your homework. Okay, so when we're looking for buffers, right, that's what we said, that's a buffer. If we want to pick a buffer, what's really, really important is not what you use, but what pH you want to get to. So let's say I want to keep my system, yes, time flies when you were having fun, I'm having a blast. So you want to keep your solution at pH 8. A lot of times our body's at 7, but there are certain cases where, or certain compartments where we want to keep a different pH. And so when you're trying to pick a buffer to use, you want to pick a buffer where you have a pKa that's close to the pH, and that's your buffering system. That's your ticket. So if I have a pH of 8, I want to pick a buffering system that has a pKa that is as close to 8 as possible. Because it's only good, this buffer itself is only good plus or minus 1 pH unit. And that's it. Okay? So I'm going to exit this. I'm going to try to exit this. I'm going to exit this. I really am. In some way, shape, or form. Clear the ink. Now exit. Woohoo! Okay. So I'm going to show you your homework. Your homework, I do need to make this bigger. I need to make this go away. I need to hide this. Okay. Now I can actually see. So if you go to Moodle, and go to our class. Here we go. So your homework is our chapter 2 discussion. Chapter 2, here, chapter 2 discussion. So I did what I normally do for you guys. Some of these do require some math, so some of them you need to show your work. Some of them are just word questions, but they're organized by your element groups, okay? And there are multiple questions for each group depending on the size of the question. Like if it was a small question, I gave you a couple. If it was a big question, I only gave you one. So in your groups, everybody contribute. If everybody doesn't contribute, I'm gonna ask everybody to put their name attached to it. But for right now, try everybody put me something, okay? And then I'll have a video posted for y'all for chapter 3, section 1 in the next 24 hours. Any questions? Where do we put our answers? So this is a, oh, I bet I didn't convert it to this one. This is what I want to do. I shared it as a PPT and not as a, anyone on the internet with this link can edit. And I bet I shared it as a PPT and not a Google Slides. Me and this technology. Me and this technology. I'm gonna get it. I promise. I'm editing it right now. Okay. When is it due by? I'd like to be able to check it by Monday before we start the next chapter. Okay. So it should now be a, what? All right, I'm gonna fix it right now. I had a typo. Oh, I had a typo. Okay, let me go back and get it. Wasn't that one, it was this one. Okay, before you go, do you want the white pages or the yellow pages? It does not matter to me, and I'm gonna go to my office and I'm gonna create a electronic place for you guys to dump them if you want to like take a picture of each page with your phone. Doesn't matter to me. And yeah, I can kind of look and see, but I can't look and see who edits which slide. I can see everybody who's editing though. You can just open the PDF. I don't want y'all to open the PDF. I don't want y'all to open the PDF. I want you to work on this. Link copied. I'm gonna fix it right now. Right now. Edit settings. Ah, is that what I did before? Did I not copy it? Come on. Copy link. Okay. Paste. All right, that should work. All right, now let's check it out. Let's see, did it work? Why is it still the PPXT? Why is it not the Google slide? I'm gonna get this. Y'all can stay on if y'all need something, but I'm gonna fix this before I go. Maybe we can copy, no, I'm gonna fix it. I'm gonna fix it. I promise I'm gonna fix it. Oh, I know what I didn't do. File, I know what I didn't do. Save as Google Slides right here. This is what I need to do. I got it. Share. Now, we're gonna copy the link, but I wanna change it to edit, and I wanna change it to anybody. And now I'm gonna copy that link. And edit it. Okay, y'all are free to go if you don't have any questions.
Dr. B.
Yes.
Okay, my question was about our lab. Whenever we go to turn in all of our lab work today,
Yes.
do you want the white pages or the yellow pages from the carbon notebook?
I want you to leave the white pages in your notebook. That means that you can do 3 different things. You can turn in the carbon copy page and staple it, right? Or you can put the white page on a copy machine and hand me a copy page, if your carbon copy is too light for me to read, if you just want to copy what you originally wrote, that's fine with me. Or you can take a picture of each page and turn it into a PDF with a PDF converter. It's like an app you can download on your phone. They have tons of free apps like that. So you can do that, and I'm about to put a virtual place for you to upload that if you would like.
Okay, thank you.
So either of three, just make sure I can read it. That's all I'm really asking.
Yes, ma'am. Thank you.
Awesome. All right, did I fix this? Chapter 2 discussion. When does Group B? Not until next week. Next Friday, August 28th, Group B turns it in. Today, Group A turns it in. When is homework due? Monday. Monday. I did not think it would take us all class period to finish clicker questions. Monday. I'd like to be able to look over them so that y'all can know if you got your answers right or not. Okay, so I'm gonna close this. Anybody else have any questions? You can turn on your thing. Will Group B have to attend? No, Group B does not have to attend a Zoom meeting. Is there a lab? Okay, Group B people, we are working on figuring out the legal situation with Labster, and theoretically, I was sent an email this morning saying that it all went through, but I have yet to get codes for y'all. So I've been on the phone with Labster many, many times over the last couple of days, and we are going to get it figured out, and we are going to get it for you. It is just taking us much longer than we anticipated. So I promise you that you will have enough time to complete all the labs that we give you, but I really don't want y'all to have to pay out of pocket for anything. So I'm really taking it to the mat for you guys. So as soon as I have information, I promise I will tell you, but I just don't have the codes yet. Any other questions about that? Good. Okay, any other questions at all? You can turn on the chat. Jennifer, you have a great weekend too. I'm thinking this is all good. Let me double check this. Y'all are awesome. Have a wonderful, wonderful weekend. Looks good. Okay, and it's editable. Yay. All right. Okay, so I guess I'm going to end this recording if I can get to it. We still have 7 participants. Are y'all good? Everybody who's still on? Y'all need anything before I close? Okay. If you need something, send me an email. I'll try to be super quick. Send me an email. All right, have a great weekend.